All right, let's get started. Last time, what did we cover last time? Relations. What was a relation? It's just a set of ordered pairs. That's it. What's a relation? Just a set of ordered pairs. Now, we talked about 5 particular properties that we were interested in on relations. Do you remember what those were? Reflexive, irreflexive, symmetric, antisymmetric, and transitive. Do you remember what all those were? What was reflexive? When every element in the set is related to itself. Right? What's irreflexive? When every element is not related to itself. It doesn't matter if you can find one element not related to itself. It has to be the case for every element. Every element has to not be related to itself. What was symmetric?
If x is related to y, then y is related to x.
If x is related to y, then y is related to x. What was antisymmetric?
If x is related to y and y is related to x, then x is equal to y.
Good. And then transitive?
If x is related to y and y is related to z, then x is related to z.
Perfect. All right. So those were the 5 that we were interested in. Today we're going to narrow in on 3 of them. That's reflexive, symmetric, and transitive. And when a relation has all 3 of those, then we call that relation an equivalence relation. So that's what the next section is called, equivalence relations. They're just relations with those 3 properties. Let R be a relation on A, some set A. Then, I think that's supposed to be an N. Then R is an equivalence relation provided that it is reflexive, symmetric, and transitive. Reflexive meant for all x in A, x is related to itself. Symmetric meant if x is related to y, y is related to x. Transitive meant if x is related to y, y is related to z, then x is related to z. Exactly like you said. So some examples of equivalence relations. Yes or no? Is the same height an equivalence relation if we're talking about on the set of people?
Yes.
Is everyone the same height as themselves?
Yes.
Yeah.
If I'm the same height as you, are you the same height as me?
Yes.
Yes.
If I'm the same height as Jack and Jack's the same height as Jill, am I the same height as Jill?
Yes.
Yeah, okay. Let's look at another one. Same last name.
Yeah.
That's an equivalence relation?
No.
Do you have the same last name as yourself?
Yeah.
If you have the same last name as me, do I have the same last name as you?
Yeah.
If you have the same last name as me and I have the same last name as Jack, do you have the same last name as Jack?
Yeah.
Ah, so it works. What about congruent in geometry on the set of triangles?
Yeah.
Yeah. What about same size on the set of all sets? Set A has the same size as set B. Does set B have the same size as set A?
Yeah.
Yeah. Does set A always have the same size as set A?
Yeah.
Yeah. If set A has the same size as set B and set B has the same size as set C, does set A have the same size as set C?
Yeah.
All right, so it works. So there's some examples of some equivalence relations. When it says prove something's an equivalence relation, you just prove it has these 3 properties. If you're trying to prove it's not an equivalence relation, you just need to show it doesn't have one of these properties. Okay, so let's look at something, well, we'll prove it's a congruence relation. It is a congruence relation, but here's a relation that we are very interested in. It's going to seem very weird when you first come across it, but it comes up all the time in number theory, and when we get to our section in the book on number theory, we're going to use this left and right, so get comfortable with it now. It's not going away. And it's the modulo N relation. So let N be some positive integer. We say that 2 integers x and y are congruent modulo N. We write it this way, x is congruent to y mod N, provided that N divides their difference. This seems like out of left field, wondering, what does that have to do with anything? So let's just get comfortable with the definition directly. Here's the exact definition, by the way. This is what you have to use in all your proofs. I'm going to give you an intuitive way to think about it. But anytime you're doing a proof with this, you have to use the definition. You can't just rely on your intuition. Right? Now, here's intuitively what we mean when we say x and y are congruent mod n. Intuitively, we mean when you divide by n, they have the same remainder. That's intuitively what we mean. So let's go over some examples, and we'll think about it both ways to help you get comfortable. Is 3 congruent to 13 mod 5?
Yes.
How do we check that? What's 3 minus 13?
Negative 10.
Negative 10. Does 5 divide negative 10?
Yes.
Yes, it works. Here's the other way you can think about it. What's the remainder when you divide 3 by 5?
3.
3. Do you remember remainders back when you were in 3rd grade doing long division?
Yeah.
When I say, what's 103 divided by 10? You would say it's 10 with a remainder of 3. That's what I mean by a remainder. 3 divided by 5 is 0 with a remainder of 3. What's 13 divided by 5? 2 with a remainder of 3. So they have the same remainder. That's another way to think about it. Take their difference. Is their difference divisible by this? Yes. Or, when you divide it by this, do they have the same remainder? Yes. Let's do the next one. Is 4 congruent to 4 mod 5?
No.
Yes.
Yes.
No, right?
Yes.
No, it is. Oh. 0. Oh.
So, 2 ways to think about it. 4 minus 4 is 0. Does 5 divide 0?
No.
I can't find an integer that I can multiply 5 by to get 0. Yes, 0 times 5 is 0. So yeah, it works that way, or think about it the other way. 4 divided by 5 has a remainder of?
4.
For both of them? Yep. All right, so yeah, that one works. What about this one? Is 16 congruent to 3 mod 5?
No.
No. 16 minus 3 is 13. Does 5 divide 13? No. Or 16 divided by 5 has a remainder of 1. 3 divided by 5 has a remainder of 3. Not the same. Right? Next one. Is 3 congruent to 12 mod 2?
No.
No. How do you know? Because 9 is not divisible by 2, or negative 9 is not divisible by 2. However you did it. Alright, this one, true or false?
True.
True.
True? Anyone think false? You're sticking with true? Seems safe, everyone else said it? It's true. What about this one, true or false?
True.
True. What about this one, true or false?
True.
True. What about this one, true or false?
False.
False. Huh?
Still on negative 14.
What were you guys thinking in your heads who were doing it fast?
Oh,
Negative,
0
negative.
minus negative 14 is divisible by 2.
Oh, I thought they saw the pattern. Are they both even, or are they both odd? Both even. Yep, both odd. Yep, odd, even and an odd doesn't work. Both odd. Yep. So mod 2 is real easy.
Oh, that's only for mod 2.
Yeah, it's only for mod 2. Doesn't work for mod 3. We happened to have it for mod 5, but we didn't have to have it for mod 5, right? Is 25 congruent to 10 mod 5?
Yes.
Yes, even though one's even and one's odd. So no, the even and the odd only works for mod 2. If they both have a remainder of 1, they're both odd when you divide by 2. If you only have a remainder of 1 or 0, if it's 0, they're even. If it's 1, they're odd. Okay, so that's congruence mod some number. We did it with 2, we did it with 5. As some examples. Now we're going to prove that this congruence mod some integer, this relation, is an equivalence relation. So let n be a positive integer, then the congruent mod n relation is an equivalence relation. So let n be some positive integer, and let x, y, and z be any integers. So first I need to show that this thing is reflexive, right? So then, how do I want to say this? Then, if it's reflexive, what does that mean? that means that n divides their difference. Right? I'm trying to get x is congruent to x mod n. Here's what I'm trying to show. When will I have shown this? I'll have shown this if I've shown that n divides x minus x, right? And I'll have shown this if I've shown that n divides 0. So then, can I just say n divides 0? Are you good with that's always true?
Yeah.
So I know n divides 0. That gives me n divides 0. That gives me x is congruent to x mod n. You good with all that?
Yeah.
So therefore, it's reflexive. 3. Therefore, it's reflexive. All right, now let's show that it is symmetric. How do we show it's symmetric? We assume that x is congruent to y mod n, and we need to use this to show that what?
Y is congruent to x.
Y is congruent to x mod n. So if I know that x is congruent to y mod n, what does that give me?
And n divides x minus y.
N divides x minus y. What does that give me?
N divides y minus x.
We can, I don't want to jump straight there. I want to use the definition of this. So since n divides this, that means there exists some integer m such that n times m is equal to x minus y, right? That's what divides means. And then I can use that to say that then n times negative m is equal to y minus x, right? If I multiply both sides by -1. Everyone see the algebra there?
What would have to be negative n too?
X times -1 is negative x. Negative y times -1 is positive y.
But would
So
n
that's
have
what
to
the
be
order.
negative 2?
What?
Wouldn't the n have to be negative? Just like the n?
I put the negative here.
But then that has to be n negative 2 because the n is
What on
negative.
earth? Okay. Look, if I know that 4 is equal to 8 minus 4, something like we have written over here, let's get different numbers here so we don't get confused. If 3 is equal to, let's actually make it a product. So we'll do 16 minus 10 is the same thing as 2 times, 3?
Okay.
Right? So that's kind of like what we have written right here. Now I'm going to times both sides by -1.
Okay.
That's -1 times 2 times 3 is equal to
Oh,
-1 times 16 minus 10.
wait, that makes. Okay.
I'm going to put this -1 back with the 3, so we got 2 times -3 is equal to, distribute through, I'm going to do my -10 first. -1 times -10 is 10. -1 times 16 is -16. So I have no clue what you guys are saying. You're really throwing me off. You want 2 negatives somehow? Okay, are we good on the algebra?
Yes.
Good thing I didn't make that leap that I thought, because I debated doing what you were thinking, and I thought, no, better walk through the algebra. Okay, so now n times something equals y minus x. That gives us n divides y minus x. That gives us
Y is congruent to x.
y is congruent to x mod n. Right? Then I think I'm not supposed to do the last part. I think that's an exercise for you.
You can still do it.
So now you need to show that it's transitive. So show that if x is congruent to y mod n and y is congruent to z mod n, then x is congruent to z mod n. I think, let me double check. Equivalence relations, congruence mod n, that's the definition. As for examples. Proof of the third section. Yep, it's left as an exercise. Okay, so can't show you the transitive, you have to figure that out. But you have an idea of how you would do it, right? You know that x minus y is divisible by n. You know that y minus z is divisible by n. You need to show that x minus z is divisible by n. Should be pretty simple. Okay, especially if you go back and look at what you already proved with your divides. Next definition. Let R be an equivalence relation on some set A, and let little a be an element in there. The equivalence class of A, denoted by these square brackets with A in there, is a set of all the elements in A, in big A, related to little a. Or in other words, the equivalence class of A is equal to the set of all x in big A, such that x is related to A. That's the equivalence class. So, if we pick some equivalence relation, like same last name for people in this room, then what is Leah's equivalence class? Leah's equivalence class would be the set of all the people in this room that are related to Leah by the same last name relation. So this would be the set of all Timpsons. Make sense? So an equivalence class is a set of all the things you're related to under an equivalence relation. So let's do an example then to see if you understand. So let's look at the mod 2, congruent mod 2 relation. What are all the numbers that are congruent to 1 mod 2? What is this equivalence class? What's in there? Is 1 in there?
Yeah.
Is 2?
All odd numbers.
All the odds are 1, 3, 5, negative 1, negative 3, negative 5. All the odd integers would be in this equivalence class. What about this equivalence class? $13.
Mod 2.
Huh?
Mod 2.
Yeah, mod 2. Same thing. Same relation, the mod 2 relation.
Still all odds.
Still all odds. It doesn't matter if I use this odd number to represent the set or this odd number to represent the set. The same way if we were talking about last name, it doesn't matter if I use Leah to represent the set Timpson. Leah's equivalence class is the same thing as Laura's equivalence class. Right? It's still the set of all Timpsons. 1's equivalence class with the mod 2 relation, equivalent mod 2 relation, is the exact same as 13's, is the exact same as negative 51's. Right? Because they're all in the same equivalence class. All the odds are together. It doesn't matter which odd you use to represent it. So we call this the representative element. 1 is just a representative element for the class. There's no reason 1's special. We could have used 13. We could have used negative 19. We could have used whatever we want. Right? Make sense? Okay, those are equivalence classes. If R is an equivalence relation on some set A, then A is always a member of its own equivalence class. A is in the set of all things related to A. How on earth are we going to prove that?
Well, we know that R is an equivalence relation, so we know that X, R, X, or whatever.
R is reflexive, exactly. Let R be an equivalence relation on A, and let A in A. Since A is related to A, then A is in the set of all things related to A. We're done. Yeah, I give you guys the hard ones for your homework, then I do these ones. Smart, huh? All right, let's do another one.
No, sometimes you give us those and you spend a long time thinking about it and you're like, oh, it's really simple.
If R is an equivalence relation on some set A, then A is related to B if and only if they're in the same equivalence class. So I'm going to show if they're related, they're in the same equivalence class, and if they're in the same equivalence class, then they're related. Let's see. 1, let R be an equivalence relation on A. Let that be 2 elements in there. Let's just show this way first. So, let's see. I'm showing that if A is related to B, then these sets are equal. So, assume A is related to B, and let X in A. I need to show that this set is equal to this set. How am I going to do that? I'm going to grab something in there, show what's in there, grab something in there, show what's in there. They're subsets of each other, therefore they're the same set. Don't be confused by notation here. These are just sets, right? And I'm just showing 2 sets are equal. I'm going to do that the way we always show 2 sets are equal. I'm going to show they're subsets of each other. Make sense? So, assume A is related to B, and let X be some random thing in there. Well, if X is in A's equivalence class, what does that give us?
X is in B.
How do you know that? What is the equivalence class A?
It's all things related to A.
It's a set of everything related to A. So if X is in A's equivalence class, I know X is related to A.
Yeah.
Right?
And then
So-
since X is related to A, then we know that X is related to B because it's an equivalence class, so it's transitive.
Because R is an equivalence relation.
Yeah.
Yeah. So then, that gives me X is related to A. Then, X related to A and A related to B gives me X is related to B, because R is transitive. And X related to B gives me X is in B. Right?
Yeah.
And similarly, we know that we could also show that
It's the other way.
we can redo this exact process, grabbing something out of here and showing it's in here, it's identical. So I'm not going to bother with that, so that's what 3 would be. So I'll skip to 4. Therefore, that set is equal to that set. Okay, now we need to do it the other way. Hopefully we can do it in one line. Assume A is equal to B. What does that get us?
A is equal to B.
Uh-huh.
That means everything in A is also B.
Remember what we're trying to show.
Does it mean that XRA equals XRB? Or they're
Well-
logically equivalent?
Let's say assume that is that, comma, then since A is in A's equivalence class, what does that give us?
A is in B.
A is in B's equivalence class because they're the same set, which gives us A is related to B. And we're done. Right? Anything weird, anything confusing, anything you want me to go over again? You need to just look at for a sec? You're just seeing how long I'll stand here if you don't talk?
How is by your saying A is in the set B, or is in the equivalence relation B, able so you can make the jump so you can make A is related to B?
What does it mean to be in B's equivalence class? This is the set of everything related to B.
Yeah.
So everything in here is related to B by definition. So if A's in there, A's related to B,
Oh, okay.
right? When we say that Laura is in the same equivalence class as you, we mean Laura has the same last name as you. She was related to you under the same last name relation. Any other questions? Okay, let's move on. Let's see what we're proving now. If R is an equivalence relation on A, and X and Y are in the same equivalence relation, then X is related to Y. Well, that's almost stupid easy, right? Let's see if you guys can just tell me. So we know that X and Y are in this equivalence relation, right? We're trying to get to what? We're trying to get X related to Y.
So we know X is related to A and Y is related to A, therefore we know X is related to Y.
Well, we know X is related to A, and, okay, you said Y is related to A. That's going to give us,
Since it's symmetrical, we know A is related to Y.
yeah, since it's symmetrical, then we know A is now related to Y.
Oh, yeah.
So we can flip those around. So that gives us, we still have X related to A, but now we have and A related to Y since it's symmetrical. And then using transitivity, that gives us X is related to Y.
Yeah.
Pretty easy?
Yeah.
Okay. Next one? All right. I got sick of writing the equivalence relation, so E dot R, that's equivalence relation. If R is an equivalence relation on some set A, and if A and B are elements in A, such that their equivalence classes have some overlap, then they're actually the same equivalence class. So if two equivalence classes have any elements in common, then they must be the same equivalence class.
Okay.
Does that make sense?
Yeah.
So we're saying equivalence classes, they either look like this, they're completely disjoint, or, well, they're always disjoint. So if you have two equivalence classes that have this element, you have the same equivalence class twice. That's one way to think about it. Equivalence classes are always disjoint. They never have any elements in common. So if their intersection is ever non-empty, you actually got the same class twice. Make sense what I'm saying? Okay, so let's do the proof of this. Let R be an equivalence relation on some set A, and let A and B be elements in A such that A and B do not have an empty intersection. If their intersection is not empty, what does that mean? That there's something in there, right? So then there exists some X such that X is in. Good thing I remembered that we need to point at the new whiteboard. Fortunately, I can still see that. Let's just move it. Hopefully, the battery doesn't die. It shouldn't. Have we only been going for 28 minutes? This is way faster than last year. You guys are worrying me. You really understand this stuff?
Big enough completely, but that's why we have homework.
It makes sense if you say it.
All right, well,
It makes sense if you say it.
I think we're covering this material a lot faster than we did last year, so a little concerning. Anyways, continuing. So, let's see. Okay, let R be an equivalence relation on a set A, and let A and B be elements in A, such that the intersection of their equivalence classes is not empty. If their intersection is not empty, that means there's something in the intersection. So then there exists something in there, call it X, such that X is in their intersection, which is the same thing as X is in A and X is in B.
What is that dot?
That was an ampersand, but I guess I'll just do like that.
Oh,
Yes.
Yeah, I meant to do an ampersand,
Oh.
but we'll just do that. Okay. So, what am I trying to get? I'm trying to get that these are equal to each other. So I need to grab something in there, show it's in there, grab something in there, show it's in there, and we're done.
We did.
No,
X.
I grabbed something that was in both of them. I need to show that for any element I grab in A, it's also in B. And for any element I grab in B, I can't just show that there is some element in both of them. Because think about this set and this set. Notice this element is in both of them. That does not mean that these two sets are equal. So for all I know, my picture looks like this, there's my x. So I need to show for any random y I grab in here, it doesn't matter where I grab it, it also turns out that it's in here somewhere. And for any random y I grab in here, it's also in here. I'm saying any random y because I'm telling you what I'm going to call my variable. So, let y be any random thing inside this set. If y is in there, what does that give me? Y is related to A. I didn't really capture the information that I should have from this. Right? If x is in A, that's the same thing as x is related to A and x is related to B. Right?
Why don't you just make that transitive? Oh, wait, you already said it.
Okay, so I have y is related to A. X is going to be my bridging unit here. I'm going to eventually get y is related to x y is related to x is related to b, therefore y is related to b, therefore y is in there. That's how I'm going to get y from here to y is in b's equivalence class. So I know that y is related to A, and I know that A is related to x, right?
Yes.
And that gives me
Y is related to X.
that y is related to x, but I also know x is related to b.
So Y is related to B.
So that gives me y is related to b, so that gives me y is in b's equivalence class, right? And we can do the reverse. For let y in b's equivalence class, that gives me that y is related to b, but I also know that b is related to x, so that gives me y is related to x, but I also know that x is related to A, so that gives me y is related to A, so that gives me y is in A. Therefore, they're equal, right? Therefore, A is equal to B. And we're done. Okay. So that's it for equivalence classes. Now we're going to move on to partitions. Now, partitions and equivalence classes are basically talking about the same thing. An equivalence class is a way to create a partition. If I say, let's look at the equivalence relation has the same last name, that partitions up my class into groups where everyone in a particular group has the same last name. When you partition something, when you partition a set, you just split it into a bunch of subsets where every element's in one and only one of those sets. Make sense?
So in this example, is each one of the subsets a partition, or is like the relation itself a partition?
The set of sets is a partition. We call the elements of a partition parts. So Leah and Laura would be in the same part. And the collection of all the students in their separate subsets, we call the partition. Make sense? So let's ignore the note for a second. So let's get down to the definition of partition now. We have a high-level understanding and look at some. So let A be a set. Then a partition on A is a set of non-empty sets. Is a set of non-empty pairwise disjoint sets whose union is A.
I have no pairwise disjoint.
They don't have any elements in common. Any two sets you grab have 0 elements in common. Okay. So, let's look at an example and then come back to the definition. Or just use the definition to answer my question on the example. So A is 1, 2, 3, 4, 5, 6. This set. Question, is P1 a partition on A?
Yes.
You sure?
Yeah. No. Yeah.
Are all the sets here pairwise disjoint?
Yes.
Yeah. They don't have any elements in common is another way to say that. This doesn't have any elements common with this, doesn't have any elements common with this, doesn't have any elements common with this.
But they have to have all the elements in A.
Yeah, when you union them up, you get A. They're disjoint. Yeah, looks like it works. What about P2?
No.
Why not?
It's missing the element 1.
It's missing 1. So let's fix it real quick. Now is P2 a partition?
No.
No. Why?
There's two.
Ah, now it's not pairwise disjoint. I can't have 2 showing up in 2 different parts. Now is it a partition?
Yes.
Yeah.
Yeah. Okay. What about P3?
Yeah.
Yeah, right?
Yeah.
Yes.
A is a set of non-empty pairwise disjoint sets whose union is A. There's an empty set right there. No, this is not a partition.
Technically, all sets have.
Not technically, no. And they absolutely do not. I would never say such a thing. The empty set is a subset of any set. That's true. Everything in the empty set is in any set, but the empty set itself is not.
It's not in the set. If you can set that.
It isn't in the subset. It is a subset. Those are very different things.
If it's a subset, then it's a
No.
We did a whole other lesson.
Here's the empty set. Here's a set containing 1. The empty set is a subset of there. The empty set is not in there. If I want the empty set to be in there, I have to do this.
set.
Okay, now the empty set's in there. Okay. So, no, we do not allow the empty set to be in a partition. So, P3, no, not a partition. If I get rid of this, is it?
Yes.
Are you sure?
Yeah.
There's not one more
Erase-
problem?
Erase the comma. Oh. No, that's good.
You see it? There's nothing to see. It's a partition.
Yeah.
All right. Just wanted you to think. Okay. So we have this relation is in the same part. So once I have a partition, then this relation means is in the same part. So A is in the same part as B means that there exists some part in the partition such that A and B are in it. So if we're looking at this partition, is 1 in the same part using partition 1 as 2?
Yes.
Yes.
Yes. So in this case, that relation is true. Is it in the same part as 5?
No.
No. Is it in the same part as 1?
Yes.
If 1's in the same part as 1, would it always be the case for any x is in the same part as x?
Yes.
Yes. If x is in the same part as y, would y be in the same part as x?
Yes.
If x is in the same part as y and y is in the same part as z, would x be in the same part as z?
Yes.
Okay, so you're going to see that this is an equivalence relation. So, is in the same part is a relation. Notice, is in the same part only makes sense once we're talking about a partition.
Yes.
Right? The same way that we can't start talking about congruence modulo N until we have an N. Right? I could just ask you, is 5 congruent to 7 mod N? And you're saying, what's N? Similarly, we can't talk about whether 5 and 7 are in the same part until we have a partition defined. So you need a partition to talk about the is in the same part relation, the same way you need an N to talk about is congruent mod N. Okay, so let's prove that it's an equivalence relation, I assume. Let A be a set, let P be a partition, then is in the same part is an equivalence relation. So we need to show it's reflexive, symmetric, and transitive. Let A be a set, let P be a partition. 2, let A be anything in A, and we need to show that A is related to A. So if A is in big A, then there must be some part in the partition that contains it, right? So since A is in A, by definition of a partition, its union has to be A, so there has to be some part containing A. So let A in A, that means that there exists some X in P such that A is in X, which gives us that A is in the same part that A is in. We just need to show it was in a part, now it's in the same part it's in, obviously.
In our proof, do we use say let P be a partition on A?
Yes.
Yeah, I just don't know if there's a difference.
On A. It's a partition on a set. You need it. It doesn't make sense to talk about a partition without talking about a set A, because I can't determine whether or not this is a partition until I know what A is. Because one of the conditions we have to check is their union is A, right? So good catch. Okay, so we know it's reflexive. Therefore, it's reflexive. Okay, what about symmetric? So let X, Y in A. Do we want to use X, Y? Let's use A and B. Let A be in A such that A is related to B. Now, if A is related to B, what does that mean?
I'm confused on why you're doing in the same part as. Like, why are you using that symbol?
This?
Yeah.
This is the relation that we're talking about. We're showing this as an equivalence relation. The same way we might show not less than or equals. The same way we might show congruent is an equivalence relation. This is just the symbol for our is in the same part relation.
Okay.
Good? Okay, so let A and B be elements in big A such that they're in the same part. I need to use this to show that B is related to A. So I know A is related to B. I need to use this to show B is related to A. Well, if A and B are in the same part, what does that mean?
There exists some.
Right? There exists some, we'll just call it big X, such that A, B are in big X, which obviously gives us that B is in the same part as A. They're in the same part. Right? Which gives us it's symmetric. Okay, now we need to show it's transitive. How do we show it's transitive? We assume that we have three elements, A, B, and C, such that A is related to B and B is related to C. We need to use that to show A is related to C, and we're done. Right? So, 5. Let A, B, C in A such that A is in the same part as B, and B is in the same part as C. Then there exists X and Y, two sets, use capital letters to help you remember that they're sets, such that AB is in X and BC is in Y. Okay, shoot. How am I going to use that to show that A and C are in the same set? or are in the same part, or are related?
Well, if A and B are in the same part,
If
then
B is
that
an
means
X,
C is
then
also
B-
in the same part.
What?
I said if A and B are in the same part, then B and C, then C is also in that part too.
It's the same one, it's just like that.
What do we know about partitions?
There can't be any overlap.
Yeah, they're disjoint. They don't have any common elements. So B can't be in two parts. So it can only be in one part. So X equals Y. Right?
Yeah.
So 7, since P is disjoint, no, since X and Y are disjoint, no, that's not the right way to say it. Since, how do we say it on a partition? A partition on A is a set of pairwise disjoint sets. Yeah, so since P is pairwise disjoint, then X is equal to Y, which gives us that A is related to C.
I'm confused. You're calling P the pairwise disjoint in this group, but in your definition it says all the sets inside of P are pairwise disjoint sets.
On a set is a set of non-empty pairwise disjoint sets. Yeah, you're right. Since the members of P are pairwise disjoint, is a better way to say it. But we ran out of room. Should give myself more space. That's what happens when I guess how big a proof will be. Do you understand why this works though? So there's no questions on how to actually do the proof. And you understand what she's saying. This isn't technically right, what I have written here. I need to say since P's members are pairwise disjoint, then these two are equal. Right? Because B can only show up in one and only one set. So the sets it shows up in are the same set. Okay. And note something I noted at the beginning. The equivalence classes of are in the same part are the parts in P. Right? If I look at the equivalence class of 1, under is in the same part relation. What are all the things in the same part as 1? 1 and 2. So the equivalence class of 1 is the part that 1 is in. There's no difference between the parts and the equivalence classes when you look at the equivalence relation is in the same part. If you feel like I'm saying something obvious, good. If it feels like what I'm saying isn't obvious, then you're missing something. All the things in the same part as 1 are all the things in the same part as 1. How else can I say it? Right? Okay. So that was just no. Okay, so how do we use equivalence classes to help us count? Because we love to count in this class. You love to. Okay, so easy question. How many different arrangements could I have of the word of this word? Word. 4 factorial, not 16. I have. It's like we're playing what's the game called? Scrabble. And I'm saying how many different words, including nonsense words, could you make with these 4 letters? And the answer is 16, right?
No.
No.
4 factorial.
4 factorial. Okay. It's 4 factorial. You have 4 options for what letter comes first, 3 options for what letter comes second, 2 options for what letter comes third, 1 option for what letter comes fourth. Okay? Now the question is, what about the word hello? So I give you these letters. Now how many different arrangements can you make?
5.
5 factorial. What if I take these L's and flip them around? Did I come up with a different word, including nonsense words? No, I didn't. So, uh-oh, it's not just 5 factorial. So, how do we think about this? The way the author suggests thinking about it, I'll show you my way of thinking about it here in a second, but the way the author suggests thinking about it is he says, imagine that one of those L's was big and one of those L's was little. You with me so far? Can you imagine that, what I drew on the board? Alright. Then he's saying, we'll divide all the words up, all the nonsense words that we can possibly make with these letters into equivalence classes. 2 arrangements go into the same equivalence class if, when I make my L's big again, they look the same. So how many ways can I get hello? I can get hello this way, and I can get hello this way. Did I lose you on that?
No.
So I'm taking all the words, and I'm putting them into equivalence classes. You with me? Every equivalence class is going to have exactly 2 elements in it. For any arrangements of letters you give me, so someone give me an arrangement.
E-L-O-H-L.
E-L-O-H-L. Okay, there's an arrangement of the letters. I'm saying for any arrangement you pick, I could have gotten it 2 ways. I could have gotten it H-E big L O, whoa, how did I start with an H? I think I looked up there and then down. Okay. E big L O H little l, or E little l O H big L. So for any arrangement you pick, there's 2 ways I could have gotten it. You with me so far? So how many total arrangements are there? 5 factorial. But then we divide by 2 because we want to count the equivalence classes. So there's 5 factorial total different arrangements, but each equivalence class has 2 in there. So when you count the equivalence classes, it's 5 factorial over 2. You with me on that? 2 different arrangements got me the 2 different, I need 2 words, 1 arrangement and 1, I don't know, permutation. 2 different permutations got me the same arrangement. How's that? So there's 5 factorial permutations of these letters, but for any arrangement you pick, 2 different permutations give me that arrangement. So when I'm counting arrangements, it's the number of permutations divided by the size of their equivalence class. In other words, we're counting equivalence classes rather than the individual words.
But you couldn't do that. Everything could do.
Well, let's do a more convoluted example. Well, let's just make a note real quick. Say in general, so let R be an equivalence relation on a finite, that's not an R, on a finite set A. If all the equivalence classes have the same size M, then there are the size of A divided by the size of its equivalence classes, that be equivalence classes, right? If A has 100 elements, and they're divided into equivalence classes of all size 10, how many equivalence classes do I have? 10. I have 10 equivalence classes with 10 members each for a total of 100 elements. Right? That's all we're saying up here. Okay, so let's do a more convoluted example. So let's say we're playing Scrabble, we've got this. These are our letters, and I'm asking you, how many arrangements of those letters can I make? How many words can I spell, including nonsense words?
8 factorial divided by 2.
Divided by what?
12.
So you said 8 factorial divided by 12. How'd you get 12?
So with the A's, it's 3 factorial for like all the different ways the A's will be arranged. And for the R's, it's 2 factorial.
Perfect. That's exactly right. And you'll see exactly how she thinks about that. So I don't like the author's way to think about small letters, big letters. I say just number your stupid letters. So pick any random arrangement of the letters. Here we go. How many permutations give me this exact arrangement? Well, I could have my first A, then my second A, then my third A, and my first R, then my second R. Or I can have my first A, my second A, my third A, but swap my R's. Right? So for this arrangement of my A's, there was 2 different ways to arrange my R's. For this arrangement of my A's, there's 2 different ways to arrange my R's, etc. For this many different ways to arrange my A's, there's 2 different ways to arrange my R's. Right? And how many ways can I arrange my A's? 3 factorial. So there's 3 factorial ways to arrange the A's and then 2 factorial ways to arrange the R's. So if I were to write out all the all the permutations that result in this arrangement, I would have written out 12. Right? So there's 8 factorial divided by 3 factorial times 2 factorial possible arrangements we can get from that. All right.
Wait, so it's not 8 factorial divided by 12.
Come on. It is.
That's what.
Oh. Yeah, sorry. Divide by 12, yeah. 6 times 2 is 12. Right? Okay. That's that. So a bunch of your examples are going to be like, they're going to give you the word Mississippi and say, how many arrangements can you make of the word Mississippi? And the same principle applies. You just count, basically, how many times a particular letter shows up. Divide by that factorial. Exactly what Emma did. So that's that. That's the end of the material. We can turn off the camera, start the video uploading, then we can do whatever homework you want.